Prove the factor theorem for polynomials of degree 2. That is, given that f of x equals ax squared plus bx plus c and k is a number such that f of k equals 0, prove that x minus k is a factor of f of x. So, a polynomial of degree 2 is a quadratic polynomial. We are given that f of k equals 0. That means if we plug k into this polynomial here, it's quadratic polynomial or quadratic expression, we will get 0. So we get ak squared plus bk plus c equals 0. So we have to prove that x minus k is a factor of f of x, where f of x is ax squared plus bx plus c. In other words, if we take ax squared plus bx plus c and divide it by x minus k, we must get no remainder. So x minus k must divide evenly into this, if you like. Or in other words, we should be able to write ax squared plus bx plus c as a multiple of x minus k. So let's look at this fraction and let's use this result here. What I can do is I can subtract f of k from the top of this numerator, and I won't change anything because f of k is equal to 0. So subtracting 0 won't make any difference. But now I can change the form of the numerator. So I've just plugged in f of k, so I'm subtracting this from the numerator. But of course it's just 0, so I haven't changed anything. Now look, we can factorize a out of ax squared minus ak squared to get a times x squared minus k squared. We can factorize b out of bx minus bk to get b times x minus k, and the c's will cancel out. X squared minus k squared is the difference of two squares. That means that we can factorize x squared minus k squared into x minus k times x plus k. So now you see that the numerator is just a multiple of x minus k. We can take x minus k out of the numerator. And we're going to be left with a times x plus k plus b, and this is divided by x minus k. So you can see that we can actually divide the top evenly by the bottom. We won't get any remainder. These cancel out, and this would be the result of our division. So there's no remainder. In other words, ax squared plus bx plus c is indeed a multiple of x minus k. Another way of saying that is that x minus k is a factor of ax squared plus bx plus c. That's what we had to prove. The factor theorem also holds for polynomials of higher degree. Now, what are polynomials of higher degree? Well, first of all, what is the degree of a polynomial? Well, the degree of a polynomial is the highest power of x in that polynomial. So for a quadratic polynomial, the highest power is 2. For a cubic polynomial, the highest power will be 3. For a quartic, it's 4. For a quintic, it's 5, and so on. We want to find the values of n for which x plus k is a factor of the polynomial g of x equals x to the power of n plus k to the power of n, where k is not 0. So this here is actually a polynomial of degree n. The highest power of x is n. We don't see any lower powers. If there were lower powers, they would look like x to the power of n minus 1, x to the power of n minus 2, and so on. So we just have a single x term in this particular polynomial and a constant term. K is a constant. So technically this is a polynomial, and we can apply the factor theorem to it. Now, the factor theorem also works in reverse. In other words, the converse is true. If we're given a factor of a polynomial, then it turns out we can find a root of g of x equals 0. So we want to force x plus k to be a factor of g of x. Then using the factor theorem in reverse, that means that g of minus k must equal 0. In other words, minus k must be a solution of this equation here. We get that minus k just from putting this factor equal to 0. Now I want to explain why the factor theorem works in reverse. We are making x plus k a factor of g of x, which means that we can write g of x as this factor x plus k times another polynomial in x, which I'm calling h of x. X plus k is a factor of g of x. That means x plus k multiplied by a polynomial in x must give us g of x. That's what it means for x plus k to be a factor. But now you can see that g of minus k is just minus k plus k times h of k. We just sub minus k in for x. But minus k plus k is 0, so we just get 0 times h of k, which is 0. So that shows that if x plus k is a factor, then minus k is a solution of g of x equals 0. In other words, g of minus k is 0. But now we can go back to what g of x actually is and sub minus k in for x. So we just copy this out, replacing x with minus k. And we want this to be 0, because we want x plus k to be a factor of g of x. By the way, n is a natural number. That means it's a positive integer. This equation here is only true if n is an odd natural number. For example, if n was equal to 3, then we would have minus k to the power of 3 plus k to the power of 3. But minus k to the power of 3 is minus k times minus k times minus k. That's minus k cubed. So you see we do get 0. Similarly, if n is 5, minus k to the power of minus k all to the power of 5 is just minus k to the power of 5. On the other hand, if n is an even natural number, say n is 2, you see what we get here. We've minus k all squared is actually plus k squared. So when we take a negative number and raise it to an even integer, we get a positive quantity. Whereas if we take a negative number and raise it to an odd integer, we get this minus sign, and that leads to cancellation. So the values of n for which x plus k is a factor of the polynomial g of x are all the odd natural numbers. So n equals 1, 2, 3, etc. Sorry, 1, 3, 5, 7, 9, etc. X minus 2 and x plus 1 are factors of x cubed plus bx squared plus cx plus d. Express c in terms of b. I'm going to call this cubic expression f of x. We know from the factor theorem that if x minus 2 is a factor of f of x, then x equals 2 is a solution of the equation f of x equals 0. So how do I get this x equals 2? Well, I get it by putting this factor equal to 0. And you can quickly see that if x minus 2 is 0, then x equals 2 is a solution. The only reason I mention this is that in some situations you might get a factor like 3x plus 4. And if you want to find out what the solution of the corresponding equation is, you set it equal to 0 and you solve. So it's not so straightforward for that particular factor. Now we know that f of 2 is 0, so we just plug 2 in for x. So we get 2 cubed, which is 8. 2 squared is 4. We get 2c here, and this must equal 0. We also know that x plus 1 is a factor. So if x plus 1 is a factor, that means that x equals minus 1 is a root. Again, we just put this factor equal to 0. And we know then that x equals minus 1 is a root of f of x equals 0. In other words, f of minus 1 must equal 0. So we work out f of minus 1. So we have minus 1 cubed, which is minus 1. Minus 1 squared is plus 1. So we get plus b here. We get minus 1c here. And then we have plus d. And this must equal 0. Now to express c in terms of b, we can combine these two equations to eliminate d. So we just subtract these two equations from each other. So we have 8 minus minus 1, that's 8 plus 1, which is 9. 4b minus b is 3b. Plus 2c minus minus c is plus 3c. Plus d minus d is 0. 0 minus 0 is 0. We divide this equation by 3 to get 3 plus b plus c equals 0. And we end up getting c in terms of b. C equals minus b minus 3. In part 2 we want to express d in terms of b. Now to do that we can combine these two equations in a different way. We can eliminate c, that's what we want to do. We want to get an equation that just involves d and b so that we can get d in terms of b. So how do we eliminate c? Well, if we take this second equation and multiply it by 2 and leave the first equation as it is. So the reason we multiply this by 2 is to get a minus 2c, so that when we add these two equations, the c terms cancel out. So here we get 6 plus 6b plus 3d equals 0 plus 0 is 0. So here's the answer. We can bring 6 plus 6b to the other side to get minus 6 minus 6b. Dividing by 3 we get d equals minus 2b. Given that b, c and d are three consecutive terms in an arithmetic sequence, find their values. So here is b, here is c, c given in terms of b, and here is d, d given in terms of b. Now, these are meant to be an arithmetic sequence. That means that if we take this term and subtract the previous term, we'll get the same result if we take this term here and subtract this term. So the difference between consecutive terms is constant. That's the meaning of an arithmetic sequence. So if we take this term here and subtract the previous term, which is b, we'll get the same result if we were to take this term here and subtract this term. So we just simplify down both sides and we solve for b. Solving this equation here, we bring minus 2b over to the right hand side, say, and we get plus b. Bringing the 1 to the left hand side, we get minus 1. Minus 3 minus 1 is minus 4. So b is minus 4. C is minus b minus 3. Minus b minus 3 is minus minus 4, which is plus 4. Plus 4 minus 3 is plus 1. D is minus 2 times b. So we get minus 2 plus 8, that's plus 6. And we should check that these terms are in arithmetic sequence. Well, if we add 5 onto minus 4, we get 1. And if we add 5 onto 1, we get 6. So that does check out. These terms are indeed in arithmetic sequence.